It's the language of the universe.
But I don't understand it.
Hello, everybody. Welcome back to another episode of the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray. And we welcome you to episode number 69, where today we're going to be talking about the fundamentals of electricity.
Not me laughing at a funny number.
Not either of us laughing at this funny number.
No.
We actually thought, why not make this, I don't know, a little bit of a meme episode, but then we're like, you know what? Let's stick to what the podcast does best. Podcast.
Wait, hold on. My mic is fucked
Oh, sorry.
already. I don't even... Oh, there we go. Okay, we're good.
Mic is good. Perfect. All right. Yeah.
Yeah, so today we're going to be talking about electricity, electrostatics. Maybe we'll even touch on magnetostatics, but we'll see. This entire topic, we've talked about this before. We had an episode called like our courses or something like that, where we just talked about like our favorite courses and like favorite exams and things like that. It was a while ago, but
Yeah.
I remember I mentioned that like my favorite topic that we did in physics was, of course, electrostatics. We learned Gauss's law in first year. That was hype. What else did we do in first year? Like
in first year, we mainly just learned just what electricity is, all the formulae, point charges, distributions of charges, and just understanding a lot
That
about
was cool.
electrostatics. No dynamics, right? In first year.
No.
No.
But yeah, that was my favorite subject, and so naturally I was pretty excited for electrodynamics in second year, which was absolutely awesome because once again you keep learning more math, and then that math just helps you even more in physics. And so you learn math, you learn physics, you learn math, you learn physics, and then it all comes together, right? You learn Gauss's law in first year, but you're doing surface integrals. In reality, you have no clue what's going on. But once you actually, you keep going in calculus, you start learning about line integrals, surface integrals, flux integrals, and what else? Stokes theorem, divergence theorem, and then you see how literally like the divergence theorem is, well, you use it for Gauss's
We're
law.
getting so complicated,
and
but yeah.
it's so beautiful. When you actually understand it, so beautiful.
What I do agree with is the beauty in all of these equations, and a lot of this electricity is where you see the application of the math. And I think we've said this so many times on the podcast. We're even though it is the math and physics podcast, we are, I think, more geared towards physics. At least I am, and I know for a fact that Parker is as well. So we have a slight larger how do I say this? Like a beauty for physics, because we apply what we learn in math into these high level concepts, and then we see what happens in real world, right? Like in math, as we mentioned, again, I don't want to get too much into that, but again, seeing its application in electricity and electric fields and stuff like that is where you can really see how such a simple topic like electricity, you see it everywhere. Such a simple topic can get so complicated,
But at the same time, it's complicated
math-wise.
You can
theory-wise.
You can break it down, right, into easier, and then you learn about Gauss's law, and you're like, hey, this can get pretty complicated. But then you start to get used to taking advantage of symmetries of certain distributions, and then it becomes so easy, it's ridiculous. You take the surface integral of a cylinder, but in reality, it's just gonna be the curved part. This is a specific example for a line distribution or whatever, but it just becomes so easy, but it's all because of the sophisticated math, quote unquote sophisticated that you're using.
So anyways, today we're gonna try to not leave it out, but we're gonna try and focus on the physics of it, on the theory of it, right? Not too much of the equations and stuff like that, but more of just the relationships of those equations and hopefully we can focus on that, right?
For sure.
So I think today's
Yeah.
episode will be really cool because I've always thought like electricity is a cool topic. So here we are, right? Before we get
Yeah.
into it though, news. Let's get some news.
For sure. For
So-
sure. Some news.
Let's start with statistics. We get downloads. We're at 161,000. Whoop whoop.
Let's go.
Almost
Let's
at
go.
200, guys. Or we beat that 150 mark. Were we at 150 last episode? I think we were, right?
No, we don't do 10K in a week.
We don't do 10K in a week, so then we
No,
weren't
not
at
yet,
150.
not yet.
Okay. Decent stuff then. Decent stuff. So yeah, we're at 150 where we topped that. Let's get ourselves to 200,000 downloads. That would be really, really cool. You know, big milestone there. 250, imagine 500,000.
Yeah,
That'd be
crazy.
insane.
Quarter.
Sorry. Quarter of a million. Sorry. You know what I meant. And lastly, our followers on Spotify still going strong at 10,800. So
Let's go.
let us get to that 11,000 mark. Always.
Quick
always looking for
reminder,
that. Yeah.
everybody, to follow the podcast wherever you're listening right now. Not only should you follow, you should go on YouTube, subscribe,
Why not?
leave a like, and also leave a comment underneath this video. Why? Because we do comment of the week every single week on this podcast. And the
sir.
winner this week is Harshad. He says, "This channel is so underrated. Should have at least 70,000 subs. The intro music makes me dancing every time." The intro. This is a side from the comment. The intro music is utterly beautiful. We've had actually some hate comments on the.
Yes, we have.
not some
We have.
hate comments.
Not hate,
Not-
but like dislike on the intro
Yeah.
music. We have had that. Yes.
Yeah. But no, we're staying strong with the intro music. But yeah, he says, "Love the informational videos. Don't ever leave this channel for God's sake." If you do, Spotify at least, but you know, we're not gonna post only on Spotify and YouTube. So don't worry, worry. We will be talking about physics on the weekly basis.
Where did he get the 70,000 from? I feel like that's such a
I
random.
don't know. I think he just multiplied by 10 or
okay.
by 100.
Okay. Oh,
from
yeah, I know
from
what
the
you mean.
subs we have. Yeah.
Well, thank you, Harshad, for a beautiful comment. And as Parker, as you just said, comment down below for the comment of the week. We're right underneath that like button. So go hit
For
that.
sure. Last
yeah,
thing
let's
before
get
we
into it.
actually get actually get into
sorry.
the podcast. This past week, we did like a poll thing on Instagram, and we have our final design that was chosen by you guys, and it's like the logo that we put on top of the Spotify covers and all that stuff, and the YouTube as well, the one with the little planet. We're going to be doing a giveaway of that t-shirt in black. So the details are going to be coming out. The details for the giveaway are going to be coming out this week on Instagram. So make sure to go on Instagram at math.physics.podcast to enter the giveaway. I think we're going to leave it open for like a week, let's say. So you have a week to enter.
Probably. Mm-hmm.
Something like that.
Yeah.
And yeah,
This is mainly for our 10,000 follower mark.
Yeah.
We wanted to do it, and a lot of people are appreciating it. A lot of people like them, like
yeah,
the
and
simple
also other people, or some people are saying like we should do every colorway with both logos and things like that, which we will do. The reason we had like the poll and you guys pick which one is because we're only giving away one for the giveaway. And just for your information, it's going to be like embroidered, like high quality, you know what I mean? It's not going to be like just like printed or, you know, whatever. Anyways, point is, we're giving away one, but eventually when we like, when we have enough like time/money to get like a website going and like the whole operation behind the merch, we will be releasing like all types of colors and all types of logos and things and whatever. So don't worry about that.
It's gonna be fun.
That's about it.
It's gonna be fun. Okay, so let's get straight into this juicy podcast. So before we
I think we start.
Oh,
Yeah.
You-
No, I think we're go ahead.
so confusing. We don't know who's gonna start. So I was thinking we start by talking, even before we talk about electricity itself, we talk about, well, what makes electricity flow, right? That is commonly known as the electron. So let's dive a little deeper into the electron and the nature of a point charge, right? So we understand now, before we get into this, right, the basics, we know that all atoms, proton, neutron, electron, and we also know protons and neutrons are huddled up, very, very, very close, very tightly knit together in the nucleus, right? So these guys are comfy. However, the electrons are always, just flying about the nucleus, depending on what model of atom, obviously, you like to choose to look at. They're flying about, and every atom has the set of valence electrons. So valence electrons are the electrons on the very last shell of any atom. Now, these electrons tend to be mobile. That means they can easily be knocked out, and one can easily be added in, right? Depending on the number of valence electrons they have. And almost every single atom has this configuration. The only ones that this doesn't really apply to are the noble gases, right? Because those have 8 valence electrons, and those guys are good. They don't want any, they don't want to let go of any, right? Now, when we come to other atoms, such as copper, silver, and stuff like that we're gonna be talking about, these guys, their electrons can be moving, right? They're free to move. So the advantage of that is when you put a lot of these atoms together and you knock one electron off, just one, it starts this chain reaction between all of these atoms that basically continuously knock these electrons off, and basically what we call the flow of electrons, right? So again, even before getting into like the whole charge and that understanding, this was, I think, a very simple explanation of what is electricity, right? So when we put these atoms together and these electrons from the last shell of these atoms are just flying together, right? So one is going to another atom that kicks the electron to the next one. Mm-hmm. So the next one kicks the electron to the next one. And it just keeps going like that until there's, one side and the other side, right? And then there's flow of electrons, which is what we call electricity.
And I'm going to use this analogy in like a couple of minutes, but it's pretty useful to think about the flow of electricity just like the flow of like a liquid. Because, it is like just electrons moving along, right? But if you look at it on like a macro scale, you kind of zoom out a little bit, it is a lot like fine grains of sand, like so fine that it's pretty much like a liquid, and I'm going to use this later on when we talk about conductors, but yeah, about it. Mm-hmm. So the very first thing that you learn in electricity is the point charge, or I think you can call it like the test charge or something. Mm-hmm. But there's two, right? There's a positive and there's a negative. By convention, it doesn't matter what you really call it, but we said that the electron has a negative charge, and we say that like the electron has like 1 unit of like negative charge, right? The actual charge is like what, like negative 1.612
10 to the negative
times
19.
10 to the negative 19 joules. Mm-hmm. But that's just like, the SI value.
Unit, exactly.
When I think about an electron, I think of like 1 unit of like negative charge. Mm-hmm. And
so that would just be electron. I mean, I don't want to. Okay, the electron volt. I thought you were gonna like kind of come into that. I don't want to.
Yeah.
Sorry. Continue.
Well, I was gonna say like there is a unit mm-hmm. called the electron volt where it, as Rehan said. But the point is that there's a positive and there's a negative. And I love, every time I talk about electricity and electrostatics, I love making the connection to gravity, because okay, you have, in electrostatics, you have positive, negative, and opposites are attracted to each other. And the equals, if you have 2 negatives, they repulse. 2 positive, they repulse. And you can set up problems where, you have a positive and a negative that are attracted to each other. And the thing is, you can kind of mix your knowledge of like gravity dynamics mm-hmm. and also electrostatics, because we had this one problem on our first year our first year physics exam, the second semester. where it was like, imagine you had a planet that was donut shaped, and then there was a moon on like the axis of the donut that was oscillating back and forth through the donut hole. And the way that I solved this was, I thought of the gravitational field of the donut as an electric field and how it was affecting a charge moving back and forth. Because essentially this wasn't a gravitation question. This was an electrostatics question. I guess you can call it electrodynamics, but I think I used Gauss's law, but you just replace the constants and it all works out the same. And that's I love those types of questions. Yeah.
So so you were talking a lot about the electrostatic force, right? And well, what is the relationship, right, between that and the gravitational force? Interestingly enough, it's literally the same thing.
Yeah, very similar.
Literally the same thing.
Very similar.
Like the equations, like for those physics guys out there that know the Coulomb's law, probably know from grade 12 first year physics. So Coulomb's law is literally Newton's gravitational law, just changing, the mass for the charge and the universal gravitational constant for the Coulomb constant. So it's literally the same thing. But again, as I mentioned in the beginning, we're not really going to be talking about the equations itself, but the relationship. So what is the relationship? And again, the fact that we know gravity has an inverse squared relationship, right? It follows the inverse squared law. So you go 2 meters away, gravity drops by a fourth. You go 4 meters away, it drops by a 16th, right? So the idea is that relationship is held in electrostatics as well, right? So it's inversely proportional to the distance squared between them. So the farther, so if you have 2 protons, or I guess let's not get into magnets, but like if let's say we have 2 protons, not that you really are playing with 2 protons ever, but that's why the magnet example would be better to explain. But in 2 protons, for example, the closer they are, the stronger they will feel that repelling force, right? But what's interesting about this force isn't the fact that there is a force itself. At least to me, what's really interesting about this electrostatic force is how, seemingly, like even with gravity, when we have things like, 5 light years, okay, maybe light years is a little too much, but like 2 astronomical units away, like the sun and let's say Pluto or like some planets, like 2 astronomical units away, there's still a force that is attracting them. Now, we've spoken in higher classes about general relativity and stuff like that, but let's just not go there right now. What's interesting about the electric definition is that there is somehow, even with like, if let's say they're 2 astronomical units away, there's still some kind of connection between them. But on gravity, it's understandable because it's space. You're on space, so what's connecting the two? Space. But what's connecting the 2 charges in the electrostatic force, right? And that would be the electric field. Right? So the interesting thing about the electric field is that it permeates through all of space. And the electron is just small excitations in this field. And the proton is similar, again, to do with electric charge, right? So the fact that they can communicate with each other even when they're like 2 astronomical units away. Again, I'm just giving a large distance. There's no significance to this number whatsoever. But when it's a large distance away, they can still communicate because of the fact that every charge emits a field. And that field, theoretically speaking, resonates through all of space. Right? And that's that. Cool.
The one thing with that is, technically, if there's a charge that's on Pluto right now, it does affect the electrons in your body.
It does.
But if you actually work out the numbers on it, because you have to plug in like the charge of like over there multiplied by the charge over here to calculate the force, as I mentioned earlier, that in SI units, which is, newtons are in SI, and so if you want to calculate like the force in newtons, you use that like really small number for charge. And so in comparison, if you have like I don't know, 1 kilogram attracting another kilogram, the gravitational force, I'm not even sure this is true, but it in my head, it appears as though the gravitational force is stronger than
It's
like,
literally not. It's the
but
same
it's
thing,
not.
though.
It's
literally
not.
the same thing.
No, it's not the same, right? I mean,
Well, because of the units, yes, because of
Yeah,
the
yeah.
units, it's a lot. Well, that's only if you're comparing electrons, though. You're
I
comparing
know,
like something
but
1
what I
kilogram.
wanted to get into, I know, but what I wanted to get into
Okay.
was to be like, oh, it appears as though the electromagnetic force is weak and the gravitational force, holds like planets together and all that stuff. But I don't know if I've said this before on the podcast, but if you take like the weakest magnet you can find in your house and you attach a paper clip to it and you you hold it above the earth, just know that the electromagnetic force holding up that paperclip from that tiny, tiny magnet is stronger than the entire gravitational force of the Earth, which I think I have said before on the podcast.
Yeah,
but
I
that's
recall
just
you saying something like this.
that's
But
that's just a fun fact.
yeah, I mean
that
that's what you
everyone
can
should know.
understand, right? Because the distance, it's all about that distance. Because when you're holding it on top of the Earth, you're 6,000 kilometers from the center of the Earth. But when the magnetic clip is literally attached, sorry, when the metal clip is literally attached to the magnet, the distance is 0, right? Because they're attached together. So like you're I mean that's that comparison, right? So there's definitely a difference in force, and the interesting thing is that they're kind of based together, and that very, I don't know if it's a meme or if it's a joke or whatever, but it's that very common thing that like Newton writing a paper and then Coulomb looking over and copying the equation because it's the exact same equation.
Yeah, it looks the same.
Yeah, because it's because it is. But again, that's just a nice thing to see in how we can compare electrostatics to gravity, right? Something macro to micro. So it's just cool.
Yeah. Here's a blessing that came down from the sky.
Oh my.
Literally. And that blessing, I don't know where we would be without it, okay?
Okay.
But that blessing is superposition.
Okay.
Because everybody's lives become super, super dumbed down because of superposition, okay? And what is superposition? You have one electron, or let's say you have a charge here, and then that charge creates an electric field. And then you have another charge that you place, and that charge has also its own electric field. Well, guess what? The resulting electric field from both charges is just the first one plus the second one. Now, of course, if the two charges are, 1 meter apart, then you have to calculate the electric field, taking into consideration where you are in reference to each charge, because the distance to each of them is going to affect the final effect to the electric field. But the good news is that you literally just have to add them up, 1 plus 1, boom. And you can do this an infinite amount of times. You can literally just say, this is my charge distribution. Let's say you have them on the 4 corners of a cube. And then you can actually take advantage of symmetry very well. Because let's say you have the 8 charges on the 4
What's
corners
a charge
of a
distribution,
cube.
real quick? Maybe just quick brief.
Well, it's like in the word, it's how you distribute the charges in space.
So there are
It's
multiple
pretty
charges.
much-
That's the thing, right? So
Yeah,
now we're no
it's
longer
just where
talking
they
about
are.
point charges or test charges. We're talking about whole distributions.
Yeah.
Right?
So you can have like discrete distributions where you have like a finite number of charges. And like this example, you have the 8 charges on the corners of a cube. You want to know the electric field at the center of the cube. Well, you can actually take advantage of the symmetry in this case, because no matter how you flip it, it'll be the same, right? So it can't be like, okay, let's say you have, you're solving this problem. You say, okay, the electric field at the very center of this cube points downwards, right? Well, here's a counter argument to that. Well, you can say, okay, well, if I flip that cube 180 degrees, is the electric field going to point upwards now? Well, the answer is no. The answer is the electric field in the middle has to be 0, because if it points one way and I flip the entire cube 180 degrees, then it has to, one, point the same way because the distribution looks the same, and it also has to point the other way because I flipped, 180 degrees. And so the only real answer, the only vector that satisfies this proposition is the zero vector. So boom. Using symmetry and rotational symmetry and all that stuff, you can show that if you have like this symmetric shape, the middle is going to have to cancel out the electric field.
And what about continuous charge distributions there? I think those get a little cool as well, right? Because the not advantage, but the difference is that there's I guess obviously you can still take advantage of symmetry depending on your shape, but the difference is that now you don't have individual particles or individual charges that you're adding or subtracting over, but you're taking an integral, right? So you're not like summing up anything, you're kind of taking a continuous sum.
Well, actually, you said I guess you can still like add them up. Well, that's like the most important thing is that you can add them up, right? Because if superposition wasn't a thing, then you wouldn't be able to really get this continuous, like the easiest distribution is the line distribution.
I just meant you can't discretely
infinite
add them up,
line. Yeah. But what you do is you treat every piece of that line as like a differential, like I'm trying to not use terminology here, but like as a very small piece of charge. And then what you do is you just sum all of those little pieces together and you see what you get. And
I remember doing this in class.
Yeah, and once again, this is like using superposition through integration, because integration as we've mentioned before is you chop everything up into infinitely small pieces and then you add those pieces all together to see what you get in the end. And so what you do to calculate the electric field of a line, you chop it and you say, okay, what is the contribution to the electric field of this tiny piece and of all of these other tiny pieces? And then with superposition, you can say, okay, well, the final result is just going to be the sum of all of that. And that's what integration does. You just sum all of those infinitely tiny pieces together, and then you get a final answer. And then the beautiful part about once again, superposition and these continuous distributions is that they can be used to find more complicated charge distributions. So for example, you can calculate the electric field of a ring charge. If you have like a ring, boom, you can do that. And then you can actually use that knowledge of the ring charge to calculate the electric field of a disk, because that's like, to calculate the electric field of a ring, it's kind of going from point charge to line charge. So you extend that point charge. And then from going from ring to disk, you go from like a one-dimensional object to a two-dimensional object. So you kind of extend your knowledge in that way. And then, of course, you can do other things. Another beautiful thing about superposition is that it goes the other way. It runs backwards. So if you have the electric field of a disk, and you know the electric field of a infinite plane, then what you can do is you can take a plane and subtract the disk, and now all of a sudden you can calculate the electric field of a plane, and you can punch holes into it, and you can do whatever you want. And you can, if you know the electric field of any shape for that matter, you can start combining, subtracting, putting all these things together, and all you have to do is put a plus sign or a negative sign, depending on what you're adding or removing.
So in school, we were going through like the electric field of these different systems of charges, right? We were going through the line charge and the disk and stuff like that. And interestingly enough, one thing that we haven't spoken about is the dipole, right? The electric dipole. It's a very, it's a very common object. It's a very common object that we deal with here. Electric dipole, it has a positive and a negative charge, and there's a constant flow of electric field, right, from that positive to the negative. And
oh yeah, we didn't talk about that.
we did not talk about that at all, because I maybe just like touching into a little bit, because including with this whole electric charge thing, again, is the fundamentals going back into what this electricity is. It's this field, right? It's this field. And what is causing all of these charges? Well, it's these field lines interacting with each other, right? When there's a positive and when there's a negative, there is a constant flow of electric field from one to the other, right? And convention is positive to negative, right? Convention is a line goes from positive to negative. That's just how we do it. But the idea, again, is if it's a dipole, it has some electric field distribution. So now we're not only thinking about how the individual charges are distributed, right? Because that could be important. But now we're looking at how the field itself interacts with each other, right? Because when we're talking about individual charges, we're just talking about their physical property, right? Like I was saying, electron, proton, stuff like that.
I mean, I don't know if I agree with that.
I mean, no, this is not an agree-disagree point. This is just pointing out the fact that the electric field is what is really causing this stuff, right?
But you're still concerned with the electric field in all cases.
Yeah.
Right.
No, but I'm talking about when we're talking about the
difference?
charges, like the electric charges and stuff like that, and we're talking about the importance of the charge distributions. I'm just saying that ties in perfectly with the fact that the electric fields are the one actually doing the entangling, right? And the superposition, all of that stuff comes from the electric field. Comes from the fact that these field lines are interacting with each other, adding, subtracting, stuff like that, right?
Yeah, but you tied it to the dipole as if it mattered. Like
no, I was just trying to give the dipole an example because we didn't do it. Yeah, sorry. No, I'm not trying to tie it to the dipole. I'm just trying to say that the dipole is something that I'm seeing that we haven't spoken about today.
Yeah.
Like the whole positive negative thing. So I just wanted to add it, and then I wanted to also add this field thing. You want to add anything about the dipole? Yeah.
Well, not really, because I mean, the only other thing, like as you said, it's a positive charge and a negative charge, and then you see like what the electric field is, what it creates, and all that stuff. Exactly. But everything other than that is just pretty technical, you know.
Mm-hmm. Exactly. Yeah. But now, understanding these fields, now we've understood a little more about their interaction. Now let's go a little backtrack a little more into the electricity argument, right? Because we were talking about that. We went very theoretical into electrons and electric fields and stuff like that. Let's get back into the world of electricity. And with like talking about these forces and moving charges and all that stuff, I think it's only fair that we talk a little bit about conductors and insulators. Because I think it's a perfect transition into talking about, well, what would amplify moving electrons and what would resist moving electrons, right? So the most common one, well, we can start with conductors, right? We have conductors that are good, so we call them good conductors of electricity, right? What that, again, basically means is that they are susceptible to electron flow, right? So any element, so for the popular elements, I'll give you the popular elements. We have copper, silver, gold, aluminum. Those are the popular elements. Why? Because their electron in their very last shell is very susceptible to move. It's very, very susceptible to move. Now, I'm not saying there are not other elements that can be used. There obviously are. But these are the most commonly used ones and the most effective ones. And we can talk a little bit about them, right? So the most common one is copper. We have copper everywhere. All wires that we see everywhere almost are made of copper. Right now, the other two, as I mentioned, are gold and silver, which are significantly more expensive. But copper, for now, is the most effective and cost-effective conductor in the world of electricity. Right? So again, as I mentioned, so what is so special about these conductors, or at least let's stick to conductors now. What's so special about copper? Again, going back to that original explanation of how electricity flows, that last electron is very susceptible to move. So as long as there are enough of these atoms bunched up together, which is exactly what is there in a copper wire, right? It's just a bunch of these copper atoms together. So when you have any kind of potential difference, right, which is what causes charges to move. So let's say you take off an electron from one of them. You just take it out, right? Then there's going to be one less here. So then this copper atom is going to want to take it from the guy on the side. And then the next copper atom is going to want to take it from the guy on the side. And then that flow of electron continues. So elements that are susceptible to this flow, that like this flow, are known as conductors, right? They conduct the flow of electricity.
And you might want to pull this up because I know you had our notes open or whatever.
Yeah.
But conductors actually have a set of properties that are very like specific and important. And I remember the first property is that there is no electric field inside a conductor.
You're right.
And I think the reason is because I think it's like proof by contradiction. Like if there is an electric field inside of a conductor, then it creates a force on the electrons, and then that creates like free energy because your electrons just start like moving within the conductor with no like reason. The second, I mean, I think there's like 5 or something. Do you have them?
Well, I mean, I just searched the properties of conductors, and I think I know what you're talking about. But like, yeah, basically one of them is the fact that they can't have an electric charge because then there's that problem, and then the others are basically just talking about the charge of the conductor itself has to be 0. So like the field has to be 0. Let me just read it off here. So it says the surface of the conductor, only on the surface the free charges exist, which makes sense. The copper. And then the charge density of the conductor itself is 0, which again makes sense, right? It's not giving out any electric charge. So yeah, so those are basically like the simple properties and what makes up a conductor, right? What we see. And you also may have seen in a lot of, I don't know if anyone probably seen CPUs and stuff like that, microchips. You always see them riddled with gold, right? So gold, interestingly enough, is in fact a better conductor of electricity. No, wait, silver is, I think I'm confusing them a little bit. But I know that, well, gold and silver both just crazy more expensive than any type of copper, right? Now, I know for a fact that silver is the best conductor of electricity. I'm a little dodgy on right now if gold is better than copper. Are you aware of this, or?
I don't know.
Yeah, I'm not too sure. But again, the idea is the same, right?
Well, it must be. It must be. Otherwise, they wouldn't be using gold. Why would they be using
microchips? Exactly. It must be better. Exactly. So anyways, as I was saying, they're popularized, in CPUs, electrical components, computer components, very, very precise components. And that's, again, why, as I'm talking, I'm going to assume that gold is better. Because why would they? Yeah, exactly. They could just use copper, right? So again, it's also because of the malleability, right?
Yeah.
There's also that could be a big reason for why it's used in microchips. Okay, so then maybe that's also a reason. But anyways, going back to the big three, silver is the best one, right? Silver conducts electricity the best, and it's all about its relationship between the outer electrons and the atom itself. So how easy can it give the electrons? That's number 1. Number 2, how packed are the atoms in the wire? That's a big one. That's a big one that not a lot of people. So it's not only about how susceptible it is to moving the electron, but it's also, and interestingly enough, about how close together these atoms are. Because I mean, if you just think about it, right? If there are 100 silver atoms versus 200 silver atoms, the 200 would be doing more electron transfer, closer electron transfer, and therefore faster as well, right? So again, it's not about so it's just about their density of atoms in the conductor as well. So all of these properties make up a decent conductor, and that's basically what it is. Maybe we can go into a little bit of what makes up an insulator. You want to take it?
Well, isn't it just
it's exactly the opposite.
It's just the opposite. The atoms are just bad at transferring electrons, and so you don't get that current flowing through. Things like wood,
paper, glass,
plastic,
like that, right?
Things like that. Yeah. There are things known as superconductors, which have a very unique property in that, like, I think the technical property of a superconductor is that it conducts electricity with 0 resistance, which means that there's no loss of energy through like friction, and I think it's like the Joule heating law, I think it's called. where like you can using like the properties of the wire or whatever, you can calculate how much energy you're losing in heat. But yeah, you see things like ideas come up like perpetual motion machines, because there's no friction, and things like trains where you can run like crazy fast trains because you essentially get like this levitation action going on between like the two metals, or I think it's like silicon boron composite, something like that.
Not sure.
I actually had like a special lecture on superconductors, but I don't exactly remember everything. But yeah, you get like this levitation where once you reach a velocity, you can just hold that velocity without using any energy at all, which is super broken. The one catch with superconductors is that we don't know how to reach superconductivity at room temperature. So we can make superconductors. It's just really hard. There's like this graph that you can search up where it's like conductivity versus temperature, and you see that when you drop below a certain temperature, some materials go from being like conductive to superconductive. And I don't remember what's the highest temperature that we've reached superconductivity, but it's not that high. And so it's a lot of work to just get to that stage. But that's one of the leading research branches that like piques my interest, because if we do reach superconductivity at room temperature, the things we can do is literally unlimited. Like there's nothing stopping us from, like, the ideas aren't even in my head. That's how crazy it is. It's like
there are a lot of there's a lot of use for superconductors. I mean, you just said the train example. Like that would be crazy. A levitating train. Like, that would be so, and that's totally possible, right? Like theoretically speaking, as long as
you just reach like a velocity of like 500 kilometers an hour, and then like you don't need any more energy, and you just hold that velocity all the way through. You can go around the world in like 2 seconds. So
superconductors right now, as you mentioned, they have that critical temperature, right? We didn't even get into resistance really. So all conductors, all this flow of electrons, there's nothing perfect, right? Life isn't perfect. We know that. The bowling ball isn't perfectly round. The pool ball isn't either. We know this. Effect of reality, right? So the thing is, it's not what was I talking about? Superconductors. Resistance, yes. I fully glitched out there. So electrons, unfortunately, do not move straight through a wire completely impeded, right? They can't, because there's some, and we just spoke about it, but there's no dramatic moment anymore, but there's some resistance, right? All conductors inherently have some resistance, right? This is simply because, well, think about it. If you just had one electron just going straight through the wire, even though I know that's not even close to how it works, that would have zero resistance. But the fact that these electrons are going back and forth between these atoms, right? Now, what happens when you take an atom out? I mean, when you take an electron out, you also ionize the atom. So sometimes when these electrons are just flying all about in these wires and in these conductors, you don't always have a perfect flow. And this is, I don't think there's a fancy term for this. I think it's just called conductor resistance. I don't know if there's any fancy thing for it. But again, all conductors have some sort of resistance, right? Resistance is measured in the famous SI unit of ohms, right? And interestingly enough, for any system that you make, any circuit that you make, you will want to inherently put some resistance into it. Now, this is because too much potential difference, and there could be then there could be a short circuit, right? Which we didn't even get into, where basically the electrons are. So in any situation where we have resistance not high enough, right? That means the electrons are not impeded enough by some material. They can just fly straight through, right? Now, the problem with that is that the object receiving this electron, right? Because usually in any circuit, there's something with the battery, and then there's a light bulb, or there's an object, or there's something that it's connected to, right? So that thing that it's connected to will receive too many electrons at once, an influx of too many electrons, and basically just cut its power out, right? So that's a nice way to think about it, and no one wants that to happen. So even though conductors inherently have resistance, resistance is good. It's not bad, right? Because we're talking about superconductors and, it's so amazing when you have zero. It's not bad. Resistance is not bad. You need it, right? Resistance, I mean, if you hook up, anyone who's played with circuits, any circuitry would know you don't put a resistor, you could really mess up your system. So you need resistance. However, in this field where we see, levitating trains and stuff like that, like there is where we could, I believe even in MRIs to actually produce those strong rays, they actually use superconductors. Again, because of the fact that there's no impeded flow, we can have, I'm not going to say infinite power, but I'm going to say a lot more power than we would have had if there was some resistance, right? So that's where resistance plays into it, and it is really important. So just wanted to clarify that even though superconductors are cool, resistance is still important. Want to clarify that.
All right. One thing that we probably should have talked about earlier is electric potential. And
yes, we didn't talk about potential at all this entire episode.
I used to hate electric potential a lot, but now I like it very much.
Oh, you like it? Okay.
Because, and here's why, okay? In electrostatics, you have like the electric field, you have the charge distribution, and you have the scalar potential. And it's like a triangle. And you have equations that can go between all three of them. So in any problem you get, you can use, like if you have two, then you can, or if you have one, you can go to the other, any two of them. And the beautiful thing about potential is that in electrodynamics, I guess, in electricity, whatever, it's a scalar value. And when you get into magnetostatics, it becomes a vector potential, which is a lot weirder to get your brain wrapped around. But let's just stick to electrostatics right now. You can kind of think about the electric potential. I think about it as gravitational potential. And how you do this is you imagine a three-dimensional map with your charges. And so imagine you just have a point charge. The map of this electric potential would be like a cone, but like a curved cone. This is hard to describe, but with the charge at the very top. Because remember, in every direction that you choose to go away from this charge, the force, or the electric field, dies down as 1 over r squared, r being the distance. And so if you can imagine 1 over r squared, the graph of that, and then make that like a three-dimensional thing, that's the shape that I'm describing right now. And so the electric potential, how I visualize it, is how high are you on that mountain, right? Because if you the closer you get to the charge, the higher up on the mountain you are, the higher the electric potential is. But remember, it's not a vector, it's just a number. And so you can do things with the electric potential, like, for example, actually this is a bad example, never mind. But I did want to continue on this like map analogy, because there are, like, it helps you understand problems that, like, if you don't really get this picture, like, to me, I remember like I said 2 minutes ago, I said I hated I hated electric potential when I was learning about it, because I remember I was in a lab last year or 2 years ago, and my TA was like, yeah, the vector potential, sorry, I keep saying vector potential. I mean, the electric potential is really useful because it's just like, it's the gradient of the electric field. And me not knowing what the gradient was, I was like, okay, nice. Thanks. Wait, is that right? Did I say that wrong?
I think that was
No,
right.
sorry. The electric field is the gradient of, is the negative gradient of the potential. And the reason, like, God, I remember being in that position saying I have no idea what that means. And now I'm in the position of the TA trying to explain what that means, and it's not easy. Because
From their perspective, it's really different.
because it's like the mountain analogy is so beautiful, because once you get it, like, it makes so much sense. And here's an example of like a problem where this mountain analogy plus superposition can help you so much. Okay, remember, let's have like a square distribution of point charges. Each one of these charges has its own like mountain, right? And with superposition, what you do is you add the heights, right? Like, let's say you want to know the potential at some point in between these charges. What you do is you just add the potential from each one. Okay, and so the map would look like, you know, this like 4-peaked mountain, and it's symmetrical on all sides. And once again, I don't know if the listeners took a listen to the episode where we talked about gradient, but the gradient is a vector that tells you the direction and the amount by which your graph is increasing the most. And so if you think about this mountain that I created in my head with the 4 charges, in the very center of this shape, you would have like a flat spot, right? Because you have these 4 mountains, and then they decrease as they come together, but it's symmetrical. And so in the middle, you'd have this flat spot. So the gradient would actually be 0. Mm-hmm. And so, as I talked about before, the cube, the electric field in the middle would actually be 0, because you get the equal contribution from every direction. But this also applies. I remember we were doing this exact problem that I'm about to describe. We did this in a problem set where you have 2 charges and you send a test charge. The question was, at what velocity do you have to send the test charge so that it lands perfectly in equilibrium in between the 2 charges that were placed? Well, if you don't think about this using the mountain analogy, it's kind of weird, because you have 2 charges, and then, you know, as you're sending in your 3rd charge, you have like some impedance because of the electric force that's stopping it. Well, I'm asking for the velocity, the exact velocity that you need so that it stops perfectly in between. And so if you imagine it like the mountain, you just say, okay, well, this quote unquote gravitational potential, you can solve it as like a kinematics question, where you roll your charge up the mountain and see how you can balance it right in between. Mm-hmm. Yeah.
Mm-hmm. Yeah, I know. I mean, that's a really nice way to think about this. Jesus, what's happening to my? Yeah, that's a nice way to think about charge in this particular way, right? Because because potential is something that we just completely skipped over, and I'm glad that we had that covered, right? Especially that mountain analogy, I really, really appreciated. We were talking about in class and stuff like that. It always helps. Who doesn't it, right? But one thing, just before we cut off this episode, I did want to get into is a very fundamental idea of electricity. And I think a lot of our listeners, even the non-physics ones, might appreciate this. Static versus current, right? That's the big question. Everyone's like, what in the hell is this thing that shocks me every winter morning, right? Like, it's a common question. And static electricity just fundamentally is different from current. And I just wanted to just briefly talk a little bit about that, right? So current electricity, also known as dynamic electricity. I don't know if it's actually known like that, but I know it like that because the difference is, again, static and dynamic. So what's the difference? So in static electricity, the reason it's called static is because there's not really a flow of current. Now, there is current, and I'm going to explain the whole thing in a second, but there isn't a lot, right? So there's no flow of current. Now, in current electricity, you do. That's why I didn't want to use the word current, and I want to use dynamic electricity, but technically it is called current electricity, so I'll continue with that. But now in current electricity, however, that's not the case, because we have current actually flowing between the battery and, let's say, the generator, let's say the light, let's say whatever in your house, right? The lamp, whatever. There's some flow of current. So what is the static electricity, right? Just brief here. So all atoms we know in our body are neutral, right? I hope so. we're not ions here. However, due to friction, right? Just walking on a carpet, and that's why carpet inherently has more friction than wood. That's why it rubs off on carpet easier. So let's say we're walking on any material that has high levels of friction. What that basically does to the atoms on our body is, remember, as I mentioned before, the electrons all the way on the outside. So the protons and neutrons aren't going anywhere. Those guys are very, very comfortable, right? The electrons are always, looking for places to go. Why not? Stuff like that. Now remember, we're still neutral atoms. So the electrons and number of protons are the same. They should be. However, when we, walk, let's say cause friction, when there's something that pulls it can pull an electron off of the atom that we are walking. So let's say we have, again, not a very good way of explaining it. As I'm walking with my socks, again, increases your friction. As I'm walking with my socks, there are atoms at the bottom of my sock, right? As I'm walking on the carpet, the electrons from those atoms of the socks are now being pulled and being stuck to the carpet. They're getting stuck on the carpet. Now, even though I'm a neutral person, my sock is still neutral, there is now a buildup of positive charge. So, if I were to ever go to any object that has a buildup of negative charge, such as a metal, for example, a metal, the corners of any metal is where the electrons can jump. So what is actually happening is really, really simple. Electrons from your sock, let's just continue with the sock. Electrons from your sock have gone onto the carpet, so now you're positive. So when your hand is coming close to the metal that has excess electrons, the electron will jump onto your sock. Just quickly do a quick little jump onto your sock.
Onto your hand, no?
Well, technically on your hand, yes. No. Because you're holding it with your hand. You're not really holding it with your sock. But what I mean is, yes, it will jump on your hand. The idea that I'm trying to get here is that you are now a positively charged person, even though you are technically neutral, just because of those electrons rubbing off due to friction. So anything that you touch that has an excess amount of electrons will then simply jump onto your body. Now, the reason it's called static is because the only thing that's really moving are electrons jumping from one another. It's not a flow of electrons. It's just excess electrons jumping from one place to another. So that is why, interestingly enough, you can't really get hurt by static electricity. It'll cause a shock for sure, but you can never die off of it. Also because we have water in our bodies, right? Very, very bad conductor of electricity there. So not really going to do much.
Die from lightning, no.
70% of people survive.
But 30% die.
30% die.
So that's still static electricity.
So let's continue on that. You kind of got ahead there. Lightning, right? So lightning is also a form of static electricity, right? Now, how is lightning static, you must ask? I see those damn currents. Isn't that a current? No. That's not current. Now, this is where it gets cool. So lightning is very, very, very similar, right? As the clouds are being formed in the sky and any situation is arising, there's going to be a split of charges where the negative charges build up on the bottom of the cloud, the the positive buildup on the bottom and the negative buildup on the top, or something like that. Some distribution because one is heavier than the other. Now, what this causes, again, it's simply about how many electrons are jumping from one space to another. It's that's all it is. So when the bottom of your cloud, right, is now lacking electrons, the exact same thing happens. It's like my hand and the doorknob. So when it finds, like, for example, a tree is a common thing that a lightning strikes simply because it's tall, right? So the thing that closest to the ground that it can attach is where the electrons will go to. What will the electrons jump onto? Well, sometimes you might even notice static electricity, you don't even have to touch it. You can just be close and it'll just jump. And you see those arcs of electricity, right? It'll just jump straight through, which is really cool. And that exactly is lightning. That is exactly what lightning is. It finds the closest spot to discharge its positively charged object, right? Very straightforward. A lightning rod, what it does is it kind of asks the lightning, hey, why don't you come to me? I dare you to come to me. So what the lightning rod does is, instead of basically, harming the house and harming your building or anything like that, it has a wire that goes straight to the ground. So the moment the lightning connects with the lightning rod, which is basically a metal, it's just a tall metal piece. When it connects with that lightning rod, it just goes straight to the ground, so it doesn't harm the building or anything like that. So that's the idea of static electricity. I just wanted to get that out there because I think it's a very common, not misunderstanding, but just people just don't understand it. They're like, well, what is this thing, right? And I don't know that, I hope that explanation was decent. I think it was fumbled a little bit there with that whole sock analogy, but I think that made a little bit of sense, right, for those people. And I just wanted to get out there that lightning itself, even that crazy thing that we see, is nothing else but just static discharge. It's just releasing its electrons or taking electrons, and that's all it's doing. So when it actually hits you, the reason 70% of people survive is also, I guess 30% people dying is not a very good number. It's still a pretty scary number, Yeah. But those 70% that do happen to survive say that, well, again, it's not the current, right? It's not the current, it's the temperature. It's the number of electrons. Because what exactly is happening? It's literally heating up the air around you, right, to cause these electrons from moving because of the amount of electrons that are there, right? It's not like your static discharge from your carpet to your sock. I'm talking about thousands and billions of these atoms that are wanting to discharge onto the ground, right? So that's where your lightning becomes so ferocious. But don't be scared by it. It's just another phenomenon of physics. That's all it is. Right? So that's that static part. And current, not that I really have to explain it. It's just, well, current is where it actually flows, right? Where you actually have electrons flowing from a negative terminal of a battery to, let's say, a positive or something like that. You have a flow of charge. So that's your difference. Just wanted to touch on that for those listeners out there.
So
yeah.
It seems as though we are slowly yet effervescently approaching the end of our episode today.
I think we spoke about everything we wanted to talk about. Yeah, we did.
There might be a part 2 to this episode. Magnets.
Oh,
AKA
yes, for sure. That would be really cool. The
second half of electromagnetism. How are they connected also? All questions that we will address later on. So if you enjoyed episode number 69 of the Math and Physics podcast, make sure to follow, make sure to subscribe, and come and like the video, leave a comment, share this with all 2 of your friends.
All 2 of your friends.
I'm kidding.
So mean. No, but also follow us on Instagram, math.physics.podcast. We do all of our updates over there. Anything you want to find out about us, DM us. Hit us up on Instagram.
Yeah, definitely. And so this has been the Math and Physics podcast. I am your host, Parker.
And I'm Ray. And we will see you soon.
Bye, guys.
See ya.